is an Apache Spark community evangelist with Databricks. He's a hands-on developer with over 15 years of experience and has worked at leading companies building large-scale distributed systems. Jules will be presenting a talk titled A Tale of 3 Apache Spark APIs, RDDs, DataFrames and Datasets. Please join me in welcoming Jules.
Thank you, guys. Thank you. Thank you for a warm welcome, and delighted to be here all the way from San Francisco. I'm going to talk about a tale of 3 APIs today, not a tale of 3 cities, San Diego, San Francisco, and San Jose, but it's going to be a tale of 3 APIs. Just a little bit about myself. I'm the guy on the left who hits the road all the time, feeling enthusiastic about talking to developers, always wear green Converse. Today I'm wearing gray, as you can see. The person on the right is my alter ego, so don't pay attention to that. But I'm really delighted to be here. And it's a way of a life for me, really, to be out here, to talk to you people, to get excited about what other things we're actually doing with Databricks and how Apache Spark is actually moving forward. And to see a crowd like you over here just levitates me, really. So as a great evangelist or advocate says, evangelism is not a title, it is really a way of life. And I take that as a way of life, of being here and talking to you guys and imparting whatever knowledge that I have and learning from you at the same time, which you actually need to make your life a lot easier as a developer. And a little bit about my company. I work for a company called Databricks. How many of you have actually heard about Databricks? How many have heard of Spark? Right, we are the creator of Spark, as Star Wars said, "I'm your father, Spark." And so Databricks was founded in 2013. The Spark project actually started quite earlier in 2009, where was the AMP Lab created by a bunch of founders who are now part of Apache Spark. Right from the very onset, right from the very beginning, our mission was really one simple thing. We wanted to make sure that everybody, analysts, data scientists, data engineers, could actually use big data application at scale using Apache Spark, and hence the community that actually has surrounded around Apache Spark, the momentum that has actually led to the adoption of Apache Spark is because of that unified platform that we actually have called Apache Spark. And what is that unified platform? Just to give you a high-level marketing diagram before we actually get into the details. If you have 3 sets of experiences, people who are working on data science, data engineers, and data analysts, they come together, working together using our analytics platform to create all these production jobs. So whether you're writing machine learning applications, whether you're writing deep learning applications, or whether you're just writing data analysis, we give you a platform so you can collaborate and work together. And underneath the platform, there is the DB runtime engine, which is supported by the artifacts that we actually see on the left-hand side, the DB.io, that allows you to get access quickly your data from the data stores. And then we have the dataless serverless machine that has, you can submit jobs whenever you want. And then at the center, at the core, is the Apache Spark, which is what I want to talk about today in terms of the APIs. What's the agenda today? Why you're here, right? I'm going to talk about 3 things. What are RDDs, which are really the fundamental data abstraction on which the entire Apache Spark was built, and then today, a lot of things are now built on top of that. I'm going to talk briefly about why structure is so important in Spark, and as a result of structure, why the emergence of DataFrames and Datasets actually that catalyzed because of that. And then talk briefly about DataFrames and Datasets, what they are, when you should use them, why you should use them. And I don't think I might have a time to do demo, but if we do, then we'll do that. And then I'll take your questions for my prepared answers. Okay, so you're not going to hear about the tale of 3 kings and the brokenness, but what you're going to hear today is the tale of these 3 APIs that make developers the new kingmakers. Because how many of you actually heard this book? This is a bloody brilliant book, right? The central argument in that particular book is Stephen Grady says that things have changed today because the APIs and the developers are the new kingmakers. In the old days, you know, the CEO and the CTO would go play golf and drink the Kool-Aid and make a decision. Now, everything is actually coming on ground up because of the open source APIs. The developers are the ones who are going to make a decision. I'm going to use NoSQL database, open source. I'm going to use Postgres. I'm going to use X, Y, and Z. Why? Because they can actually bring those 2 together because of open source. And that's the reason why the developers are the new kingmakers. And right from the very outset, we knew that if we wanted Spark to be the next thing, who do you talk to? Who do you win the minds and the hearts of the people? It has to be developers. It has to be people like you, right? And that's why APIs are central to earning the mind share of developers, and that's why they're the new kingmakers. So let's look at the first set of APIs, RDDs. People have used RDDs, right? That was the first thing that Apache Spark was created on, which is the resilient distributed data set. That's why they're called RDDs. Well, what are they? You know, they have certain characteristics. And as I say, they were the fundamental logical data abstraction on which the entire programming model was built on. And so if you can think of your logical structure, it's a huge data set that you actually read from the HDFS, from S3, or from wherever, and it's distributed across the cluster into small partitions. And each partition is made of all these different RDDs. So they're distributed in nature, and as a result of that, you can actually do functional programming. You can execute your code in parallel, and they will execute on each and every partition, which is part of the RDD. So they're a distributed data set. They're resilient, hence the name. And they're immutable. What do I mean by that? Now, resilience comes from the fact that if you look at RDDs, there are two kinds of operations you can perform in RDD. You can do what we call transformations, that they emerge from one RDD to the next one, to the third one, to the fourth one. And that lineage is called DAG. So at any point, if something happens, if something fails, I know where I came from because I have a lineage. That's why they're resilient. They can recreate themselves. They're immutable, which means that if I make a transformation from A to B by doing some operation on it, the original RDD remains unaltered. The new one just gets a new set of values. And that's how we actually create the lineage. And that's what I mean by resilient, and they're immutable. They're lazy. Not in a slothful manner, but they're lazy in the manner that they don't materialize themselves in memory until a certain action is created, until you trigger the entire DAG to be executed. And that's what I mean by they're lazy. They're compile safe. In other words, RDDs have a certain type. You know, you can have an RDD of strings, you can have an RDD of binary data, you can have an RDD of numbers of integers, a double or whatever. So they have a type associated with that. And as a result of that, it gives you some sort of a compile type safety. And they can have structure, or they can have semi-structure, right? So they can be both, either structure or semi-structure. And then finally, if you had to look at visually, this is what your typical RDD looked like. This is what you guys used to work before Spark 2.0 came over, before DataFrames came over, before structure was introduced in Spark. This is sort of free-flowing text, right? You could have things coming from social media. The logs do have a structure, but according to RDD, it's just a string of lines. And then you got free-flowing Twitter. Or you could have structure, which could be something like DataFrame that actually has name columns, and each and every name column has a type associated with that, and we'll see how DataFrames actually looks at that. But for RDD, it's just a string. And then you, as a developer, would have to figure out what field is what, and what should I cast into in order for me to do something. So that's what it is all about. Well, why use RDD? You say, well, we as developers are control freaks. Is that true or false?
Yeah, absolutely.
Thank you. One person democracy. We as developers are really control freaks. We like to tell how things should work. We want control. We want visibility. We want to make sure that everything actually works. So if you're a developer, which you are, most of you, and you love control, and you love flexibility, that's why you use RDDs. Second, low level. Extremely low level API. These are the assembly language of Spark. Think of it in that, if I can use that particular analogy. Some of you are C programmers, for example. In C programming, you can actually, remember in the old days, you can actually introduce £SM sign, I'm dating myself, and you can actually introduce assembly language. That's what it is. They're very low level. And the typeset, as I already mentioned. And then because of the first two, the corollary of the last thing is that they encourage you, or they nudge you, or they somehow force you to tell Spark, to instruct Spark how to do something, right? Which is what developers really love. Now here's a sample code. Let's look at this particular code. This is a code from our training class. And what we're trying to do over here is that we're reading a huge Wikipedia file that is a text file, and what I really get back, since I'm using 1.6, I'll get back an RDD, right? An RDD is just this big logical abstraction over my entire cluster. And the next thing I'm going to do is I'm going to perform several operations. Remember I talked about operations, transformations. Flat map is a transformation, so I'm doing a flat map over here, and I'm saying take that particular line that I actually get one at a time, get all the lines up, split the lines at the end of carriage return, and then match against this particular lambda expression that I have. If I have 4 fields in that particular line, then give me this another object in Scala called sum, which is of type any, and it will have 3 things in it that are matched. If I don't match that particular thing, then just drop that thing, right? So that's what my first transformation happened. So my first RDD was this original RDD. The second RDD was parsed RDD, right? The original remains unaltered. I can always go back and recreate it if I actually wanted to. So that's what my DAG looks like. The second thing I'm going to do after I've done that, I'll go ahead and say, okay, I really don't care about all the other languages in the Wikipedia. All I care about is English. So I'm going to filter out only English pages that I care about. And so I'm going to do another map over here using the filter saying, given parse RDD, match this particular case with 3 arguments, make sure that I only get the English one, which is the project that I care about, and then match against the 3 items and give me the tuples. I care about the page, and I care about the number of requests, because we're trying to count the number of Wikipedia requests on that particular page. And then what I'm going to do is I'm going to reduce my key, which is nothing else. They take all the pages which actually have the same keys and add them up together. So that way I can keep aggregation of all the pages of the same type for number of requests. And now I'm performing an operation called take. Now take is an action. Nothing that I've done so far will happen until this particular point, where the DAG is materialized, and I'm going to take the first 100 items, and I'll just do a for each loop. Lot of code, right? But we got control. We're telling it exactly how we want something to be done, right? That's what the power of RDD. So then you ask, well, you know, there's nothing wrong with that. Why should we use RDDs? Well, because you want low-level control, and in your data set, as we actually saw right now how the code was showing us, you don't care about dealing with structured data, right? You just have one data, you're just going to pick up the string, and then you know exactly what your data looks like, and you'll pick up individual fields because you have prior knowledge to that, such as media streams or text or log files. You want to manipulate the data in the manner how you can actually provide lambda functions. And you saw all those lambda functions where we were doing case statements, and that's where you actually want to use lambda functions, as opposed to what we call DSL, which are domain-specific, high-level APIs that you'll actually see the data sets in DataFrames and SQL offers, which you're telling it rather what to do, not necessarily how to do. And you don't care about the schema, right? I don't care whether my first field is an integer, or the second field is timestamp, or the third field is date. I'll figure that out when I need to, when the time comes. And then you can sacrifice the optimization and the performance and the inefficiencies that you might not get the benefit of using the higher level APIs, which we're going to get into momentarily, and the inefficiencies that you might introduce that you think you're actually telling Spark how to do, and you'll do it because garbage in, garbage out, right? So what's the problem now, you wonder? Well, the problem is that when you're dealing with RDDs, you're very much wrapped into how to do something rather than telling Spark what to do, because Spark is smart enough to figure out for yourself that you're trying to do something I'll optimize for you, because we have combined all the most recent technologies borrowed from high-performance compilers and high-performance databases and optimized engines, so we know what to do, right? If you tell us what you're trying to do, rather than you telling me how to do, I'll just do it what you tell me to do, right? So we can't optimize in Spark. If you don't tell me what to do, what you're trying to do, what you're trying to accomplish through these high-level operators, I can't optimize for you. If you don't care about that, c'est la vie, right? They can be slow. In non-JVM-based languages such as Python, RDDs are slow, because we pickle the lambda function, we send it out to an external Python process which is running in the same JVM as your executor, and that Python get executed, sends you back the results. So there's an extra layer of interaction that actually goes, and hence they're actually slow. And then the inverted inefficiencies that you enter. What do I mean by that? Well, look at this particular code, right? the 2 lines of code over here that we are doing, which we have introduced inefficiencies. It's the same code that we actually looked earlier where we are filtering that down. What do you think the problem is over here? You see those 2 lines? Right, what we're doing over here is we're doing a reduce by key on the entire data set. And then we're saying just filter out the things I don't care about. As opposed to, why don't you just filter out half of the data set that you don't care about and then do reduce by key. When you look at this particular code, it's completely innocuous, right, for you, because you're so close to it, as opposed to, you're telling Spark what to do, and the Spark will pick that up. So this will actually create a lot of, if you have a huge data set, you're going to bring in the entire data set into your memory across all the clusters. It will do the reduce by key, and then you say, okay, I'm going to do a filter now. Then you do another shuffle. Whereas opposed to the other way around, we say, I'll get rid of all the data I don't care about, and I just do a reduce by key on a smaller data set. So those are some of the things that can actually introduce in your RDDs, and you probably want to avoid that if possible. But if you know what you're doing, just like anything else in life, if you know what you're doing, then you do it. So that's where structure in Spark enters. And this is the new set of APIs that we actually introduced in 2.0 called datasets and DataFrames. And there was a reason for that. And the reason for that was that we realized that in order for us to reach a larger set of developers, we have to extend that functionality so that data analysts who are familiar with Spark SQL, people who are Python programmers who can actually express their queries in a relational manner, which is very similar to some of the DSL functions that you do in SQL. And we wanted to build our entire structure engine based on the structured APIs. But before I talk about structure, let's look at something that's unstructured, such as RDD, right? We talked about RDD, and RDD Spark knows that RDD has 3 things. One, it has dependencies, because it knows how to recreate itself. I talked about all the transformation and how the RDDs work. And then second one is there's a partition associated with an RDD. So there's a notion of data locality. So if I'm assigning a task to the executor, I'm going to send it to the disk or to the executor that actually has the data. So there's a notion of what we call data locality. And there's a third characteristic associated that Spark knows about, that is called compute function. And given a compute function in RDD, I'll get back an iterator, and then I'll just iterate over the lambda function across the entire cluster on each executor. So those are the 3 characteristics that actually make the Spark's programming model. What's the problem with that? Jules, what's your problem? Here's a problem. Right? This part is opaque. Right? We don't know, Spark doesn't know what you're trying to do in this particular compute function. Right? You're giving me a lambda function. The least I can do is I'm going to create that as a stream of bytes. I'm going to send it to the executor, let it execute it. I don't know what sort of data is in there, and I don't know what you're trying to do, right? I don't know whether you're doing a filter. I don't know whether you're doing a sort. I don't know whether you're doing an average. I don't know whether you're doing a sum. However, on the other hand, if I knew that you were doing that, I could actually optimize the data. If I knew that your data type was certain types safe, I could actually optimize that because I can store the data off memory in a more efficient manner using our tungsten generation code. So that's the particular problem. And this is where we decided to say, okay, we really need structure in Spark. And what does structure in Spark give you if you were to look at it from the compiler analysis point of view? It's a spectrum, right, from left to right. SQL, if you express a query in SQL, it says select X, Y, Z from a foo where certain predicate is met. If you make a mistake, a syntax error, or you misspell the column name, or you misspell the Spark, the SQL operation, you won't get that error till runtime. So everything you've done so far, all the hours of work, you executed the last particular query, and it'll happen at runtime, which can be quite expensive, right? Whereas if you go a little bit towards the right, the data frame, which has methods, and they have some type associated with that. If you misspell the method name, right, if you say filter to something else, you're going to get a compile time error. On the contrary, if you provide a string name as a name of a column that doesn't exist, you will get runtime error. And then on the far right, you've got the more fascist one, which is datasets. And it is very compile type safe because it knows that you are actually dealing with a certain data type. And if you provide a lambda function, the lambda function will actually have type associated with that. So when you execute that at compile time, boom, you're going to get an error. So you actually save a lot as you go from that particular spectrum. So I just wanted to throw that out to you, saying that that's what it is. So what we did in 2.0, we actually combined everything in one data frame. right? One data frame was that you have data set, a data frame which was introduced in 1.3, this came in 1.6, and we said, if you just have one API that does everything across all the workloads, developers have to worry less about it, and data frame just became an alias for data set. So if you do something today in your data set or data frame API, you're going to get either data frame, which is a data set, or bro. And then in Python, you don't have data frame, you don't have data sets because Python is it's not a static compiled language. Here's a very simple code in data frame. We're doing exactly the same thing we did with our RDDs, but look at how easy it is. I can take my RDD and convert that into a data frame with the name called project, page, and num request, and you will know exactly what type it is, because the first one is a string, the second one is a string, the third one is an int. I can do high-level operations, such as group by, which was what we were trying to do by reduce by, and I say, well, filter them out with English, group by the number of pages I care about, sum all the requests that I have on that, and then put them in a column called count, and then limit that by 100, and then show me. Is that easier to read? So much easier to read, right? So much easier to express. And Spark can actually optimize that. And you can actually do something more, right? You can actually take a data frame and convert it into a table, and then actually use Spark SQL to actually query the same thing. That gives you that particular benefit. So why structured APIs? They're easy to use. Look at how easy it is for me. I know exactly what you're trying to do, so I'll optimize that. I can actually express the same thing. Book. See that? I mean, if you're a control freak, you love that. Developers love that. Sometimes you don't want to use RDDs, which is fine. There's nothing wrong with that. I'm not trying to put it down. So what happens underneath the hood in 2.0 with these 3 sets of APIs? They go through transformation, right? The transformation is that it doesn't, I don't care what sort of API, what API are you using SQL, using data frames or data set. They go under the transformation whereby the catalyst will take your logical plan and create, during the analysis phase, 2 things. One, it will consult the catalog to find out what table you're trying to access or what column names are. If those are resolved, it'll go to the next stage. And then it'll try to create a logical optimization plan, followed by what we call a physical plan. And then you can see at the end, what happens is that the code generation, which is the tungsten part, generates the final version, which is what? RDD, right? So RDDs are here to stay, except that they've been subsumed by these high-level APIs. And because of the fact that it goes through this journey all the way to a very close machine level code, we exactly know how to optimize that. And there's a lot of work being done in this particular area by guys who actually spend their entire years PhD dealing with code optimization, dealing with JIT compilers, and dealing with how do you actually rearrange the code in a manner that actually helps you. Here's a very simple query whereby I'm trying to join 2 particular tables, and I get this particular logical plan, right? Where it says, okay, go in and scan this table, go in, scan this user table, join them together, and give me a filter. And it goes through the optimized version and says, I can actually rearrange this code. I really don't care about it. I'm just going to scan the events from one table. I'm going to take the users from another table. I'll filter on the predicate, and then I can do joins. So I have less data to deal with. The physical plan comes in and say, are you nuts? I can actually optimize that by saying, optimize the scan events. What does that mean? What it's going to do is going to push it down. We call predicate push down. I'm going to push it down to the database to which you're actually trying to read the data. And the reason some of the databases are very optimized to do filtering, so it's going to do a push down predicate, convert that into an SQL query, send it down to, let's say, MySQL or RDMS, whatever the database, get those scan optimized, same thing over here, and then do a join. Less data comes in, it knows exactly what to do. If you were doing this RDD, you lose that optimization. Here's a very simple case of the dataset API. They're type safe. They're just like RDD. They have actually a string associated with. I'm going to read something from a file called people.json. It has a couple of fields in it. I'll try to infer the schema. And then what I'm going to do is I'm going to convert that data frame into a data set based on the case class. So now I have a typed data set that I know exactly what the first column is, what the second column is, what the third column is, and so on and so forth. And if I was writing a lambda function, or if I was writing a function that I was giving it to filter, I can just use this notation, which we are very familiar with, right? If you're using a Java bean, you would actually use that. If you're using a C++ class, you get an object, and you're going to access that object using the dot notation. So much easier to use, so much easier to read. And What are some of the other benefits? Why you actually want to use datasets and data frames? Now here's an example. You can see RDDs are a lot slower. Even in Scala they're slower, but in Python a lot slower. Why? Because we have an external process whereby we actually do that. And the numbers are quite fast if you were using any of these in 2.0. Right? This is all 2.0 stuff. They use less memory. Why? Because in tungsten encoders, we actually have a better way of serializing and deserializing code. And we can store our internal format, which is off the heap. So we're not using the Java heap to create objects. We're using our own internal mechanism to create the data set. So when you're doing the caching, you specify or you occupy less space. And data sets are a lot faster and because of the fact that we have actually encoders. So you ask, well, why use DataFrame? Because they're high-level APIs. You will see the benefit in telling something what to do as opposed to how to do it. And you can actually use domain-specific language such as SQL to define. You can define your own operations on top of that. And that gives you an immense power. Yes, you lose a little of flexibility. Yes, you lose a little of control. But at the same time, you get the benefit of using high-level operations, and you get the optimization with it. They're very strongly typed, as I say. Data sets are very strongly typed because you can actually define the type that you want. They're easy to use. Code is very easy. And here's the most important part. You're telling Spark what to do. And once you tell the Spark what to do, I can optimize the code for you rather than you trying to do the code, because we have lots of experience optimizing code at the very low level. There's a lot of work being done, there's a lot of research being done today in the academic world in how to actually use the most optimized parallel compiler technologies to do code generation. So once you tell me what to do, you're creating a sum, you're creating a filter, I'll be able to do it. You have some of the scenarios, right? If you care about structure, if you care about schema, you want to define a particular schema, this is when you actually want to use the data sets and data frames, because you're telling Spark, here's what my schema looks like. I have an integer, I have a string, I have a boolean, I have a timestamp, and then I have something that just could be a string of bytes. You care about code optimization because you want to do things fast. You want to run things in parallel. You want to let Spark do most of the work for you rather than you sweating yourself. Space efficiency, because of the tungsten code generation, we have a lot of encoders that when you define a data set with that particular case class, we have an encoder that actually stores that space efficiently rather than using the Java serialization, deserialization using on the hip. We do it off the hip. And here is what the future is going to look like, right? Going forward, everything is going to be built on top. In other words, everything is going to be decomposed to RDD, but you can actually see there's a layers. There's a catalyst that's actually sitting up here. You got data frames, and then ML pipelines, which is the 2.0 library for machine learning. You actually create data frames when you create your pipeline for fitting the model. You actually get data frames back. Structure streaming is entirely based on data frames. The way we look at structure streaming is nothing but an infinite table of data frames that actually come continuously, and you start operating on it analytically as data comes in. That's why structure streaming. Graph frames, again, is an equivalent of GraphX, which is RDD based. We are moving more towards graph frames. In 2.2, just about a couple of weeks ago, when we actually had Spark Summit, we introduced 2 open source initiatives called deep learning pipelines that sit right up at the top. And as more things come in, that's where we're actually heading. So visually, if I actually had to put everything together, this is what it looks like. If I had a Venn diagram, data sets is the universe of everything. We got RDDs, which are very functional programming. So we provide a lot of lambda functions. We tell Spark exactly what and how to do something. The data frames go a little higher, where you use a relational and catalyst optimization to do that. When you're looking at data frame, it's like as if you're executing an SQL query, and then you've got the data sets at the top. Unfortunately, I don't have time for the demo, but there's a Spark Summit coming up soon. Any of you been to a Spark Summit? Brilliant. Yeah, so if you like Guinness, we're in Dublin. Do come and visit us. Great people. If you're a fan of James Joyce, it's a great museum for that. This is a definitive book that's actually coming out in September. Spark definitive guide written by none other than the creator of Spark and one of our product managers. This is 2.0 going forward. Everything you actually heard about today is in that particular book at much more deeper. You can actually get a couple of chapters if you actually follow the particular URL. And I believe that these slides are going to be available to you sooner or later. Is that correct? Should be, yeah. And finally, this is really a talk which is I wrote this particular blog called A Tale of Three APIs, and I borrowed some of the stuff from my esteemed colleague who is a trainer. And this is really a combination of those two. This is the vocalization of the blog, and this is some of the concepts that I actually borrowed. And these are the two URLs you can actually use to go further and get deep into that. Here are some of the other resources that you actually have, which are great for you to know more about DataFrames and RDDs. I know I'm not doing justice in just half an hour to push all this stuff down to you, but there is immense amount of information over here that you can actually go home, and this could be either cure to insomnia or cure to euphoria, one of the two. And then obviously, as Henry Christian just said, do you have any questions for my prepared answers?